primary reason we use confidence intervals and discuss these ideas statistically is to then implement good decision-making skills that are not just based on gut feelings. I want data-driven decisions. Like what? Should I change book companies? Should I change? I'm buying textbooks for next year. Should I change my book supplier? I produce cans. Where should I get my metal from? We talked about rebar and concrete. Where should I buy that? Should I invest more money in this program? Yes or no? I need some sort of idea. Should I do this? Shouldn't I do this? What's the best place option? And then I need to go out and check the data and say, does the data support what I want to do? Yes or no? Now, there are lots of different ways to do this, and they depend on the way in which we construct our hypothesis. So what I need to do is I need to make an assumption. I need to gather the data. I need to use that data to test the validity of my hypothesis. And either the data will support my hypothesis or it will not support my hypothesis. Then I can refine the hypothesis, retest, and this becomes a decision-making cycle. Page 318, we have this sort of ongoing process. I get an idea, I create a hypothesis about it. I gather the data, I do some statistics, I decide. That's the piece here. After I've tested my hypothesis, I make a decision. And once I'm done, this whole cycle starts all over again. Because no decision is ever absolutely 100% final in an environment like this. Okay. There's some detail in here I need to figure out about what exactly goes on here and how I create what my hypothesis is, what sort of data I gather and what I collect, compute from it, and how I use that to decide. So there's some things I need to fill out here. The hypothesis I'm going to create, this assumption of mine, is called the null hypothesis, H sub 0. And its opposite is called the alternate hypothesis. Now, some books use H1, some books use HA for that. This textbook, I believe, uses H1. So These hypotheses need to be completely exhausting and mutually exclusive. I've heard those terms before. What do they mean? Emily?
Collectively exhaustive.
Right. What does that mean to be collectively exhaustive?
The two of them that it covers all of it.
That's completely exhaustive. They cover all the possibilities. Mutually exclusive.
Don't affect each other.
That's independent as opposed to exclusive. Completely exhaustive means they cover all the options. Mutually exclusive.
There's no intersection.
Yes, but also. Either one happens or the other, never both. Never both. They exclude each other, and never something else. This is the only thing that can happen. Either H0 happens or H1 happens. Ne'er the twain shall meet, nor do we have any other options. So something like a security system. Either I have the passcode and I get in, or I don't. A drug test. It tested positive or it tested negative. Inconclusive means something fucked up and we got to do it again. A jury trial. You are either found guilty or not guilty. That's the result of the trial. You can't be both, can you? So I form this set of hypotheses. Most often, the null hypothesis is that everything is okay the way it is. And the alternate hypothesis is I need something different. We'll look at more specific examples as we go along. I go and I gather data. If my hypothesis is about, we were talking earlier about sourcing metal for cans. So maybe I'm like, I need to have at least this purity level. The amount of contamination has to be less than 5%. Well, then I'll go and I'll analyze a bunch of them and I'll look at the proportion of contaminants. Okay, then I'm asking a question about a proportion. I gather data and I look at that statistic, the proportion. That's this step. And now I need a decision rule so that I can use to test my hypothesis. I say, oh, I look at this information, and if, then I will say, use the alternate hypothesis. I reject the null and use the alternate hypothesis. So maybe I look at all that metal samples and I say, oh, the proportion of contamination is too high. I shouldn't change suppliers. Or the proportion of contamination is, well, if it's too low, that's a good thing, right? I should switch suppliers. So I calculate some test statistic from my data that's related to my hypotheses. the sample of hair I took from this person contains chemical tracers consistent with drug use above this level. The security code you typed in has this many digits that are different, or this many transpositions in it, or whatever. A fingerprint, biometric data, right? You unlock your phone with your face. What if you get a black eye? Does your phone let you in? I cut myself shaving. I'm wearing a bandage. Will my phone let me in? I have too many points of discrepancy between the stored image and my face. I have a problem. I can't get in my own phone. So once I get my data, I have to decide how good is good enough, what consistency level I need. Or equally, I could think of what level of inconsistency will cause me to reject my hypothesis. This is a decision we get to make. How good is good enough? Where have I heard that idea before? How confident do I want to be in my answer? This is the linked confidence intervals right here. I'm looking at confidence levels. How confident am I that it's close enough? Then I make that decision. I say, based on my level of confidence that I want and the data I gathered, I will do, if I see this number, I'll say yes. If I see this number, I'll say no. Our null hypothesis is not proved. It's accepted, and it's whether or not I can reject it. We don't actually prove anything with these sorts of tests. We just can disprove stuff. We can't prove it. Most of the time, I can test the hypothesis more than once. There's an exception to this. We talked about a guilty, not guilty idea. You can't be tried for the same crime over and over. That's called double jeopardy. If you get found not guilty, we're done with you. But most of the time, I can test something multiple occasions. I can go back and I can test a hair sample for the presence of drugs multiple times, as many times as I have hair. I can test the similarity between my face and the stored picture over and over by repeatedly lifting my phone up until it recognizes who the hell I am. I continue to demonstrate that my data supports my hypothesis, but I can't actually say it proves it. So this is the process. Questions? Because there should be a lot of them coming. Let's consider what could happen. Errors in decisions and outcomes. I am going to make a call. I have two possible things that could be true. Either my null hypothesis is true or it's not. So those are the two possibilities. Problem is, I don't know which is true until I do a bunch of investigating, right? Well, I'm going to do this investigating, and then either I'm going to reject my null hypothesis, or I'm going to say, no, I'm not going to reject this. Please note that's not accept. We really only talk about accepting or rejecting or not. We don't talk about accepting here. Okay, so let's suppose my null hypothesis is true. If I am in this first column, where's the I got it right box? Right here. Good choice. And in the second column, it's the upper box as opposed to the lower box. This is a good choice. But it is possible that I could be in one of those other two boxes. We've used these terms before. We talked about drug testing. If the hypothesis I make is true, but I reject it anyway, that's called a type 1 error, commonly referred to as a false positive. If it's false, but I don't reject it, that's a type 2 error. A false negative. If I put this in terms of one of our examples, drug testing, what's a type 1 error do? My hypothesis, you are clean. My hypothesis is you are clean. What's this do? So we DQ'd you as an athlete. You're not allowed to compete this year. Or you don't get the job. Or you get arrested. What's this? In that drug test setup. They got away with it, right? They snuck in. Somebody set the home run record this year on monster steroids, right? Somebody got the job. What happens down the line? I don't know. But the test gave us they were clean. I didn't get a flag, but it was wrong. Let's go to the guilty, not guilty verdict, right? Null hypothesis. Null hypothesis is innocent until proven guilty. You are innocent. That's my hypothesis. What's this mistake?
They were innocent and you sent them to jail anyways.
That's not good. What's this mistake? They got away with it. Whatever it is, it could be murder, could be a speeding ticket. I don't know. They got away with it. Now, clearly, this is in our current system. This is less bad than this. The current judicial system says it is better to let 10 guilty people go free than put one innocent person in jail. That's why the presumption of innocence exists. a security person, a security code, badge. You have to tap in and out to get in the doors of this building, right? So you're allowed in. My null hypothesis, your badge should let you in to this building. What's this mistake? Boop, and nothing happens. Boop, nothing happens. What's this mistake? So here's a question. Which of those is worse? That one's a little harder than the jury trial idea or the drug test idea. So that's a discussion we're going to have to figure it out. Let's do some probabilities. This looks like one of our contingency tables, doesn't it? I'm going to call the conditional probability, the probability that I reject the null hypothesis, even though it's true. I'm going to call that alpha. But what does this mean? What is this the chance of based on this table? It's a chance of a type 1 error. We're going to call this number a level of significance. Now, clearly, if this is a probability, what do I know about this as a number? What do I know about every probability as a number?
Plus the one,
And
and the opposite will be equal to one if you have the.
so it's between 0 and 1. It could be equal to 1, but it's between 0 and 1. The opposite. Failing to reject given it's true. Yes, 1 minus alpha would be the opposite of alpha because they have to add up to 1. Similarly, beta is the probability that I fail to reject the null hypothesis given that it is false. So now we're doing the same idea, but in the second column, this is the chance of a type 2 error. Now, beta itself is not often called something, but its complement is. 1 minus beta is usually called the power or the sensitivity. A more powerful test means a smaller chance of a type 2 error. Yes? More power, less beta. But that means there's less here. There's almost always more here. There's a trade-off between alpha and beta. My problem is I want to have tests with small beta. I want high power tests. I want tests with small alpha. I want them to have few false positives. I want to be able to get it right as often as I can. More powerful tests will lower beta, but they do so at the expense of making the rejection part harder. And if it's harder to reject, then things can slip through here. Crap. Smoke detectors. Y'all have a smoke detector in your house, right? It should be in your bedroom or right outside your bedroom. Why?
I want you to wake up.
The alarm is going to be right there. It's going to get my ass well. Great. If I make a more sensitive smoke detector, what happens? Even if there isn't smoke, it's more likely to sense other aerosolized things like hairspray, a hairdryer, because the hairdryer blows little particles of skin and hair off of you, which aerosolize and sets off the detector, especially optical detectors, which use a little beam of laser. And when enough stuff is in the way of the laser, it goes, ah, there's smoke in the air. The more powerful my smoke detector is, the more likely it is to give me a false positive. It'll go off when there's no smoke. And fire drills at 3 o'clock in the morning suck. And that's bad too, because then it's like you don't have one in the first place. More sensitive COVID tests keep healthy people at home. Why? They're more sensitive. We're not going to let people who are clean, who are sick out. But that means that people who are not really sick end up staying home too. The more sensitive any test is, the more powerful it is, the more likely it is to generate a false positive. More often, though, I'm more concerned with type 1 errors than type 2 errors. So I'll choose a significance that I'm willing to bear the consequences of. Now, here's the unfortunate truth. That level of significance is made up. It's one where I say I'm willing to bear the consequence of being wrong and having a type 1 error. What does that mean? It means usually I can pick an alpha level, like I want to be 95% or 5% or 10% problem. I'll only have a type 1 error 5% of the time. I'll have a type 1 error 10% of the time. I'll have a type 1 error 1% of the time. Gee, these all sound like familiar looking numbers. They're confidence levels. And then I say, all right, I can do that. But then to reduce my type 2 error, I need to gather more and more and more data. And that means longer and longer trial testing periods. We got COVID tests really fast. Why? Because we needed them now. Couldn't afford to wait. And so we sent out very powerful, very sensitive tests. And people all over the face of the planet tested positive. And some of them really were sick, and some of them were just on the edge of a little ill. And I had a different virus, but it showed up anyway. And the tests were really powerful because dealing with the consequence of a type 1 error meant you missed work for a couple days. Okay. The consequence of dealing with a type 2 error, you made a whole crap ton of people sick and somebody died. I don't like that idea. But if I run more tests, I can make the false positives smaller and I can make the sensitivity better. But then you don't get the test as fast. How many of you have gotten a flu shot or are planning to get a flu shot this year? Have they tested the flu shot? Kind of.
They've tested past samples of the flu shot, but they change it every year because the flu mutates every year.
And so this is what we think the flu is going to be. So we're going to give you these particular immunizations because we think those are the proteins that are going to be triggering with the flu virus. The virus itself has proteins on the outside, and that's how it sets off your defenses, or how it gets past them, in the case may be. But if I don't actually run a blind test, you have the flu, you come in, I give you this shot, it either makes your symptoms better or not. If I don't run that blind test, I won't know. And I won't know how accurate that flu shot is until March. Did I do a good job or not? I don't know in advance. Should we give flu shots based on that? Well, I think sure as hell yes. But other people disagree with that. And that's the current war over immunizations. What consequences are we willing to live with? Problem number 5. What is the consequence of a false negative in an inspection of your car's brakes? Please note it says right here, the null hypothesis is the status quo. Things are okay. So, the null hypothesis, your brakes are fine. What is a type 2 error in that situation?
Your brakes are fast. Yeah.
If my null hypothesis is that my brakes are fine, being in the type 2 column tells me my brakes are not fine. A type 2 error, my brakes are not fine, but I think they are. I go in and I get my brakes inspected. The guy goes, no, your brakes are fine. I go out. Bad idea. What's a type 1 error in that setting?
Tires are messed up and but they're actually fine.
Brakes, not tires, but yes. I think they're messed up, so I get a brake job and I spend money. Now, if I'm a mechanic, I want you to spend the money. If I'm the car owner, do you want to spend the money? Well, not unless I have to. So to me, as a car owner, a type 1 error might be expensive, but a type 2 error would be more expensive, wouldn't it? So we have to make a decision as to which errors we think are more acceptable than others and pick these numbers appropriately. But since I am working in the realm of statistics, my hypotheses are going to be about statistics. A statistical hypothesis is a statement about some parameter in my population that I want to understand things about. So I could be asking you about the mean of something, or the variance of something, or the proportion of something. Most common tests are about mean and proportion. So we'll focus on those. A hypothesis test is a decision-making strategy. It's the decision rule for our null hypothesis versus my alternate hypothesis about our parameter. Yes, ma'am. Rule. A decision rule. That's a bad U joined up with my L. So if I say in my population, the average is 5, then I go and I take a sample. What should I expect to see? There's more to the sentence that I haven't written down. I say the mean is 5. I go take a sample. What should I see?
The hypothesis of the population being 5, other hypothesis where it is 5.
Aha. So I can say my hypothesis is either the mean is 5, I'm right, that's my null hypothesis, or the alternate, it's not 5. But when I go do a sample, what do I see in my sample? I don't know how many people you're going to sample. I don't know how big the population is. I don't know how big the sample is you're going to take. I'm going to run with the idea that I'm going to do an effectively infinite population appropriate size sample. So maybe I've got, 20,000 people. I'm going to go ask 50 of them. That's a small enough percentage. Good. But I should get a sample mean, right? I should get an average out of my sample. And that should be close to 5. That's the problem statement right there. Close. Maybe I'll get 4.9. Maybe I'll get 5.1. Maybe I'll get 6. Maybe I'll get 13. Maybe I'll get 2. I don't know. Maybe I'll get 5.03. No idea. But I can now ask the question, how close is close enough? This is sampling, right? This is a random variable. This has a PDF. In an effectively infinite population, this PDF looks like a normal distribution. So I can now ask, is the sample mean I got way far away from the average I expected based on my chosen level of confidence? In other words, are these in a confidence interval together? If they are, then I think I'm right. If they're not, I must be wrong in my assumption. I should reject the null hypothesis you came up with, Tony. There's my decision rule. My decision can be made about the sampling distribution of my mean or my proportion, depending on what I'm looking at. Aha. If they're not in the same confidence interval, then I'm probably wrong. So I've just figured out how to make my decision based on my desired level of confidence, my assumption about the population, and my ability to do a confidence interval. Our null hypothesis is going to be based on some value. In this example, it was 5. And I literally pulled that number out of my ear. But what I can say is I'm going to have some sort of benchmark. Maybe I've got past data, prior knowledge, industry standards, targeted values, product specifications. In some way, I'm going to know what number I should be aiming for. So we're going to make our hypothesis based on our claim about our mean or our proportion for the population based on some particular value. Most of the time, we're just going to call this the null value. So I'll call it mu sub 0 or pi sub 0. In the problem I was just looking at, I picked 5. And again, that's our benchmark. Again, I tell you to go home and flip a coin a dozen times. If your coin is fair, I should expect you to get 6 heads and 6 tails. So let's say I'm counting the number of heads. Then my assumption is that that number should be 6. My proportion should be 0.5. But that value, that benchmark, came out of some knowledge of the experiment we are doing, some knowledge of the coins and the way that coin flipping works. If I am working with production lines, we're filling product containers. Chocolate chip cookies. Anybody want a cookie? I had some at lunch. Chips Ahoy chocolate chip cookies used to have a logo on the bag. And their slogan said, anybody know the slogan for Chips Ahoy cookies? 1,000 chips in every bag. Were they correct or were they lying their ass off to us? I kid you not, a statistics class at a high school tested this. They got a whole bunch of cookies and they washed away the cookie dough and left behind just the chocolate chips to find out if there really were 1,000 chips in this bag. They didn't just do it once. They did it a bunch. And then they said, I have an assumption that the average number of chips in a bag is 1,000. Then I went and gathered data. And now I can say, are these two close enough? Yes or no? That means that for my parameter value, I can figure out a choice for our null hypothesis. And we're going to start with means. For a mean mu, there are 3 possible versions of H naught and H1, the null hypothesis and its alternate. I could say that the average is bigger than or equal to my benchmark. I could say the average is equal to my benchmark, or I could say that the average is less than or equal to my benchmark. These are the three different versions of H0. Each of them has a corresponding alternate hypothesis. For this one, what's my alternate hypothesis?
Less than.
Benchmark. Remember, it's got to be mutually exclusive and it's got to be completely exhausting. I covered everything bigger than or equal to. Now I need to cover what's left. Here, what's my alternate hypothesis for this version? Perfect. And for the last one, mu is three different options. I'm going to call these by the alternate. This is called a left tail test. This is called a right tail test. And this one is called a two-tail test. Other than what sounds like an appeal to furries, why would I call these things by tails?
On the graph, don't have a long tail on one side or another.
Almost. It's not the length of the tail. Because if I'm doing sampling, what distribution am I looking at? When I do sampling, what kind of distribution does my sample have? My X bar. It was the whole reason we could do confidence intervals the way we did. It's normal, which means it's that bell curve. So I'm asking, what's the chance I'm down far away? And if I'm down far away, then I should be in this picture on the left of my curve. If I'm asking about being up on the right, oh, my average is bigger than mu zero. But in the middle, it's just not equal to, right? So it's split in both directions. Now, there's something really important in these pictures. Please notice how they're all labeled. The white unshaded area in each picture has a value written in it. The value written in it is 1 minus alpha. What was alpha again? What did we call alpha? That was a chance of a type 1 error. So we gave it a name and we called it a level of significance. Alpha is the significant. So what's 1 minus alpha? That's a chance we didn't make a type 1 error. And not making type 1 error means we got it right. That's the insignificant part. It's only a significant thing if we're in the little bitty pieces whose total area is alpha. Our level of significance tells us what chance of rejection is. And if my number falls in this part, I'm going to reject. If my number falls in this part, I'm going to reject. My number falls in this part, I'm going to reject. This picture on page 325 is going to become one of the Bibles of our doing statistical tests. I need to know what these cutoff critical values are. That is where we will start next time. I will see you all then. Have a wonderful rest of your day.